Hello, Dr. J here, helping to demystify statistics one video at a time. And as you can see from the date on the top left part of your screen, I am starting the new year with all of you in statistics. That probably says a little bit about my personal life, but that's okay, because we're here to talk about descriptive statistics. This is a really important one, folks. No matter what kind of research study or anytime you talk about any type of statistics, this is going to be your foundation. And it is from this foundation that you can go on to other types of statistics, right? But if you don't do this, you wouldn't not do it. So we have to talk about this foundation. So here we go. The basic outline is, what are descriptive statistics? And then the types of descriptive statistics. Nothing too fancy here. Okay. In terms of descriptive statistics, what we're talking about are things like mean, standard deviation, percentile, and they're just mathematical ways to describe something, hence the word descriptive. And that's why I've used our friend Bob Ross. For you younger viewers out there, you may not be familiar with Bob Ross, but you might be, because he painted beautiful landscapes and he talked about them with his afro, and it was fantastic, well, his fro. But really, he was just describing what he was doing, describing a landscape. So it's very simple. These type of statistics are describing our sample. What is the average? How much variation is there around the average? So they're descriptive. And you can see here that we're referring typically to a sample. So when we say the mean or average, we're really talking about a sample. It's impossible for us to get an average of the entire population. It's usually difficult. So most of our descriptive statistics, like average and mean, are talking about a sample. You can see here, these are descriptions only, and in no way are we going to be able to draw conclusions or look for a relationship. And because of that, we're not going to be able to apply to a larger population. Now, from these descriptive statistics, we can take the next step and try and draw conclusions and look for relationships and try to make inferences to a larger population. So we do the descriptive stats first. I don't care if you are doing something really small, a sample of 5 people, or whether you're working at a R1 research institution and you're doing a big funded research study. It doesn't matter what kind of numbers or what kind of information we get, you're always going to do the descriptive stats first. And a lot of this is simple, but some of it, like standard deviation, people don't understand when it really isn't that difficult. But this is a great foundation. And if you don't get this foundation, it's going to be more difficult to move on to our inferential. So after we do our descriptive stats, and only after we do our descriptive stats, are we going to be able to move on to inferential statistics, where we're trying to make an inference about a sample to a greater population. If that sample is representative of a population, in other words, if these descriptive stats that we get from our sample, if they demonstrate a normal distribution, that normal bell-shaped curve, well, then we're going to be able to make inferences from that sample to a larger population. But if our descriptive statistics show a ton of outliers, show really inconsistent data, then we're not going to be able to make very good inferences. We may try, but we may not be able to make very good inferences. And by the way, these inferential stats, it's all the fancy terms, the t-tests, the ANOVAs, the regressions, all that fun stuff. But everything comes from the descriptive first. So here is your summary table, because as you know, I like to use summary tables, but we've got 4 categories of descriptive statistics. and we're going to talk about all 4 categories. We're going to start with our summaries of data. So our first category of descriptive statistics are pretty basic summaries. And what's included here would be frequencies, graphs, tables, and histograms. I'm noticing this white might be hard to see against the background, but you're going to see these other places, so not to worry. These basic summaries are really there to make data easy to understand and see. A simple graph or table can be used to highlight the most important information. And yes, even as people doing statistics, we want to get our readers interested. So if we can have a simple visual summary or a simple table, that's going to capture our readers' interest, hopefully. Considerations for this is not the time or place to be fancy, folks. Keep it simple. If you get into the habit of reading a lot of research studies, sometimes you see they're just trying too hard, like a 3D bar graph with, you know what? I can probably better see just a regular old bar graph. If your information is cool, then I'm going to want to look at the bar graph. But no fancy bar graph is going to make boring information interesting. So keep it simple, and then just choose appropriate tables or graphs, and use appropriate scale, obviously. So we're going to let Bob Ross here, our little friend, walk us through all of these types of descriptive statistics as we go along. He's our bullet man. Instead of bullets, okay. Frequencies. This is a simple summary of data that we need to have. We need to see what is the total number of subjects in our sample, and that's N. Maybe, like in this table here from SPSS, my total N in my total sample is 20. And then I have smaller groups. I have a smaller group of women of 10, and I have a smaller group of men at 10. Well, this is pretty important information. If I'm looking at a study, I want to know how many people were in their sample. What were those samples broken down into, right? Sometimes, as this table shows us, you might see a percent. So we can see that the subset, the small n of men, made up 50% of all. That can be useful too. Another way we can provide descriptive information is a table. Look at this simple table. This came from my dissertation years ago. It looked at the protocol for the peak VO2 test. So we started off from warm up to 3 minutes at 50 watts of resistance, and then we went up. Very clear. No need to be fancy. You can see we always include units, so we have watts, and then we have minutes. Fantastic. When you're actually writing something up, we tend to have certain rules that we kind of follow. So when you're writing up a study or a lit review or whatever, if you include a table, you're going to want to reference it in the text. As we can see from table 1, or you could say, the protocol used in the research study is described in table 1, and that'll point the reader to it. And oftentimes, you'll even want to highlight at least one data point in your write-up. So I may say, the protocol used in the bike peak VO2 test is described in table 1. The watt went up to a maximum of 325 watts. Something simple. Okay, we can also use a pie chart. So depending on the information, maybe a bar chart is better, maybe a line graph is better, or maybe a pie chart. A pie chart specifically might be better for our nominal or categorical data. It's a nice, simple, easy summary. Now you can see this is pretty boring, right? It's grayscale. So oftentimes when you submit something, for example, this is APA format, it's got to be in grayscale. But, we do the best we can. Now we also have a histogram. And this might be something that you're not familiar with, but once you start to perform some research studies, this is something that's going to become your friend. And listen, I'm not too shy to say that histograms are important, and they've been my friend many a time. All right, here we go. When you do any kind of dependent variable measurement, and you're using an interval or ratio level of measurement, if you have questions about that, please refer back to my video on levels of measurement. These are going to be specific data values that are ranking, that have an absolute 0, right? For every dependent variable, you're going to want to use a histogram. And along the y-axis is frequency, and along the x-axis is your dependent variable. So this is an example of age, right? So I have age from age 15 to age 45, and it just shows you the frequency of values along the x-axis. So each histogram only shows one variable. We're not doing any calculations here. That's why it's just a summary of data. This is not going to show me the mean necessarily in the graph. Oftentimes it'll be reported on the side, but most importantly, this is a visual summary of each dependent variable. And oftentimes, particularly in SPSS, it'll draw in this line, and you can see in this dependent variable, we got a nice bell-shaped curve. So we can see right off the bat that our ages had a pretty normal distribution. The majority of the subjects in my sample fit into the middle, with fewer people of higher and lower age at the end. You're not going to use this in publication. This is for you for data screening. So I can see what my dependent variable looks like. Is it distributed normally? Are there a lot of outliers? Because based on that, and by the way, that process is called data screening. Based on that screening of your data, you may have to make some corrections. You may have to adapt the data a little bit. Maybe you cut out some of the outliers. Maybe you transform them logarithmically. These are all tricks that we can use to better make inferences in our next type of statistics. And of course, if you ever do any data trimming or data removal, you would report it, right? Sometimes you may get a histogram that looks so out of whack that your dependent variable isn't even useful statistically. That doesn't mean that it's not useful, because we still learn something, but it may not be useful to move on to the next step of inferential statistics. So you're going to like that, folks, believe me. You're going to see I have a video coming up coming up soon, on the normal distribution. And this is what we look for, that bell-shaped curve. But this video is going to also talk about what do you do when it's skewed one way or the other, when the curve is too high or too low. Check out that video. We would ideally like to see as many histograms that look like this, but come on, data is data, so we're definitely going to see some that are skewed this way, or some that are skewed this way, or maybe you'll see kind of a flat distribution, or a really tall distribution. And all these things are things that you need to look for. But check out the other video. I know. I mean, what else are you going to do this year, right? Okay, so our first example of descriptive statistics was our summary of data. We can look at frequency of our subjects and then subgroups of those subjects. We can look at tables and graphs and histograms. Our second example of descriptive statistics would be measures of central tendency. Everyone knows mean, right, folks? So mean is our best example. Pretty much for whatever data we're gathering, both the independent and dependent variable, if you're able to calculate a numerical mean, you are going to want to calculate a numerical mean. And because we're fancy, we don't say average, we say mean, right? But we also may find useful the median. If we line up all of our values for a variable in a straight line, the median is the exact middle value. And we may also find use for mode, which can either be defined as what is the frequency of each value, or what is the most common value? I mean, pretty simple. Mean means average. The good things about mean is that it represents all the data, right? So if we have 10 scores along a spectrum, the average, that really tells us something about the whole set. What was the average? Even though there were some high values and low values, everything is incorporated into determining the average. However, averages or means, they can be affected by extremely high or low scores. In reality, you're almost always going to report the mean. But if we find that in our histogram, right, we could still have a mean, but what if we see that's a bad drawing, Dr. J. What if we see along our data points, most are in the middle, but then there's some out here and some out here? Well, the mean tells us about what the average score is, but it doesn't tell us about the outliers. This is when you may want to use median. So if we line up all the scores in numerical order and we find the value that's in the middle, it may give us a different number. So if our average is right in the middle, but our median is maybe down here, it tells me something, right? But the median may not represent all the data. So to sum it up, we're pretty much always going to use mean. If we notice that there are a lot of outliers, we may report mean and median. Mode is not used as often. I tend to do research that is physiological, so I have a lot of numbers that are interval or ratio level of measurement. But for those of you in the softer sciences or other disciplines, and I don't mean to say softer is pejorative, it's just different, like a social science or psychology where you're measuring things that are not assigned a numerical value, you're going to be using more of nominal and ordinal levels of measurement, which nominal and ordinal levels of measurement are categorized as categorical data. You may be more inclined to use mode. In other words, when you give a survey out to a group of people and their responses aren't numerical, maybe you ask them how they feel about a certain thing, you may be interested in the mode or the frequency that they use certain words. All right, cool. Here is what an SPSS outlook might be like. We can see already some of our examples of descriptive statistics. Here we see the N, which was a summary of data. And then here we see our mean, median, and mode, which would be our measures of central tendency. Now, we're going to start to see a pattern. So we already talked about summaries of data. That was number 1 that I've deleted from this slide. We just talked about measures of central tendency, mean, median, mode. And now we're going to move on to what the category calls measures of variation or dispersion. What it really means is variation. And we tend to record these together. So we may have mean plus or minus standard deviation. You may see mean plus or minus standard error. So we tend to give our descriptive statistics in combination. So whenever we report a central tendency number, we're almost always going to report after it some type of measure of variation. And this is our most common combination, right? Mean plus or minus standard deviation. Now, don't freak out, my people. Listen, I'm not sure if I've said this before in a video, but I'm going to say it now. I never really got stats until I was in school for my PhD. And that is just because maybe I didn't have the right teacher. I find that a lot of times teachers at institutions of higher education are very smart statistically, but maybe aren't as good at teaching. They're so smart they just get it, and they're not very good at explaining it in simpler language. But when I was in school for my PhD, I had a teacher, a professor, who was fantastic. And for the first time, I was like, oh, that's what it is? Okay. So a simple example of that is standard deviation. I mean, many of us have heard of that, and we've seen, maybe even that 68% of the data tends to fall within plus or minus 1 standard deviation. 95% of the data is going to fall within plus or minus 2 standard deviations. But, what the hell does that mean? Well, that's why I'm here in honor of my grad school stats instructor. I want to pass this along to you. So let's really make sense of standard deviation. Before we do that, we're going to be talking about range. Range is our really simplest form of a measure of variation. Now, we're going to discuss range and we're going to discuss variance and standard deviation. There are other examples of ways to measure variation, standard error of the mean. We're not going to discuss those. But all three, what they tell us is how the data points or how the values vary around the mean. If we know the mean, that's the average, right? These are my data points along an x-axis, right? But what's also important, it's not just important. It's not enough just to know the mean. I want to know, where are the other data points fitting in? Are most of them clustered on the side in equal amounts? Or maybe the mean's in the middle there, but the other data points are over here. So this gives us more information. How do all of our values, how do all of our numbers from the sample, how do they vary around the mean? Maybe they vary a lot, and there's some up here and there's some down here. Maybe they don't vary much at all, and they're all clustered around the average or the mean. So think about a dartboard. If the center, if the target is our mean, any measure of variation is going to tell us where all the other darts are. Are most of the darts clustered around the mean? Are they towards the target? Maybe a really good dart thrower? Not me. Or if it was me, I would have a lot of the darts out here, and there would be more variation around the mean. Hope this is making sense to you. One example of a measure of variation, the simplest form, is the range. It tells you what your lowest value was all the way to what your highest value was. Here's an example of an SPSS readout. It's going to give us the mean. So in this example, we had 524 in the sample. Just ignore the missing for now. We'll talk about that in the data screening. But I had a sample of 524 scores. And the mean of those scores was 42.17. The standard deviation was 13.3, which we'll talk about. But look at the range. The range was 79. So it means that the distance between my lowest and highest number was 79. If I was good at math, I would do that. You'd think I teach statistics, I'm good at math. But this just tells you the range from the lowest to the highest number. It has limited usefulness. I mean, we do want to see the extremes, but it doesn't tell us much beyond that. Let's talk about standard deviation and variance. Now, when we talk about these, we're going to tend to talk about them together, even though there are some differences. Both of these have the same definition. And we're going to be talking mostly about standard deviation because that's what we talk about most often. Standard deviation and variance refer to the average variability of scores around the mean. Therefore, if I have a high standard deviation, that means that there's a lot of variation of scores around the mean. So if I have my x-axis and here's the mean, a higher standard deviation means that I have a lot of scores out here and I have a lot of scores out here. There's a lot of variation. A lower standard deviation means that there's little variation. So if I have my x-axis and I have my mean, if it's lower standard deviation, all my scores are going to be much closer to the mean. There's not much variation. I mean, we can think about different populations or things that are going to have a high and low variation from the mean. If we look at types of haircuts in the military, it's going to have a low standard deviation. There's not that many types of haircuts. Most people are going to have a buzz cut, or for women, shorter hair. But if I look at type of music people like, there's going to be a large standard deviation. Maybe the majority of people like pop music, but there's so much variation. There's country, there's rap, there's this, there's that. This is a really important thing to look at. The mean gives us a useful data point. Well, what's the average? But then the standard deviation expands our view. So in addition to knowing just the average in our data sample, now we know, well, how are the other data points clustered around that average? If it's a high standard deviation, there's a lot of variation. And that means that we're going to have clusters of data points everywhere, far from the mean. A lower standard deviation means that there's less variation. Most of the data points are closer to the mean. For me, I just memorized a definition, and this is what made sense to me. Average variability of scores about the mean. If there's a high standard deviation, the scores vary a lot from the mean. The mean is the same, but other scores around it are spread out. In a lower standard deviation, same mean, but we would have scores that are more clustered around the mean. Now, let's get into the weeds a little bit. When we use standard deviation most often, we are referring to a population, and our standard deviation is in units of the variable. If it's age, then the unit would be years, right? And this is what is used by researchers. So this is what we talk about, right? Now, if you're a statistician, if you're really a numbers person, statisticians are going to be talking more about variance. And in variance, we're talking about a sample. And in variance, the units are squared. Now, I've given you the formulas just so you can look smart if someone's looking over your shoulder while you're studying this. And I want to make another point. Whenever we're doing stats, whenever you're running statistics, even descriptive statistics, we're going to end up using both. It's just that you're going to be reporting the standard deviation. This is what you report, right? If you have an abstract to a paper. The purpose of this study was to examine types of music enjoyed among different age groups. And you're going to report your means, right? The mean age was 25 plus or minus 2.3, right? Which would be, the mean age was 25 plus or minus 2.3 years. So most of the people fell within 25 plus or minus 2, so 23 to 27. That's what you report. Behind the scenes, whether you do it by hand, if you're forced to, like I was when I was getting my PhD, or if you let the computer do it. Behind the scenes, you're going to need to be using variance. And I'll talk about why in a minute. Because this allows us to do more inferential stats down the road. So they, in essence, mean the same thing. Most often, we're going to report standard deviation, which is in the units of the variable. And then variance is something that we use behind the scenes. And really, all we do is we take the standard deviation and we square it. Okay. Excellent. So, as I've already said, standard deviation and variance, it's an excellent follow-up to the mean. The mean gives us some information, but it doesn't tell us where the other data points are. So standard deviation tells us where the other data points are around the mean. So here's some simple examples. Here we have 4 ways to plot a sample. We have the same number of dots in all 4. And in all 4, the mean is 4.725. So in all 4, if I could draw a straight line, that's our mean, right? But these show you different standard deviations. If we look at A and D, in these samples, they have a lower standard deviation because more of the dots are clustered around the mean. The lowest standard deviation is A. D has a little bit higher standard deviation. And then B and C are examples where, even though the mean is the same, the other data points are much more spread out. There's much more variability of scores around the mean. So again, mean just tells us the average and that's it. But we need standard deviation to get a sense of where the other data points fall. Are they clustered together? Low standard deviation. Are they more spread out? Higher standard deviation. How about some real life examples? Well, I'm recording this in the first day of 2021. We are in full COVID time. So if I apply the same thing to age, COVID-19 occurrences by age, maybe the average age is 64, right? These are a little bit off kilter. This should be over here. But you get my idea, right? The average age might be 64, but different states, for example, may have a different standard deviation. So maybe here, maybe I say New York, right? New York, all of the cases are more closely clustered around the mean. But if I look at California, it's the same mean. So on its face, you may say, well, New York and California, they're the same because the mean is 64 years old, the average age of people who get COVID. But when I look at the standard deviation, I can see much more information. In New York, it's more people in and around 60, 64, 70. But in California, we see a much bigger range. So we may need health organizations, health professionals would need to look more at, well, why in California are more younger and more older people getting COVID? Another example, and I don't need to have the COVID on here, but it is, think about exam scores. Here we have 2 groups. Both have an exam mean of 71.5. But as a teacher, or even as a student, these are very different. As a teacher, I might be happier with this one, where there's a lower standard deviation, right? People overall did better. Versus group B, where I'd be more worried. The average looks the same, but there's so many more outliers. Good examples, my friends. I know. So how do we interpret standard deviation? Well, as I said before, when we report our data, and of course, this is a basic reporting of descriptive statistics. This is where everything starts from. The first part of understanding a data set is seeing its description. What's the average? And how do the other data points, how are they arranged around that average? So we're going to report often mean plus standard deviation. Here's age plus or minus standard deviation. So if these were subgroups, A, B, C, D, E, whatever the case may be, if these were subgroups, this is showing me the average age plus or minus the standard deviation. what this standard deviation actually means, it really depends. There's not one set good or bad standard deviation. It would be impossible because remember, standard deviation is in the units of the variable. If I'm looking at age, I might consider a certain standard deviation to be good or bad. In fact, all of these are pretty good. That means that if I wanted to get a good sample of someone around 22, I did that because my standard deviation in my sample was plus or minus 1 year, basically. So most of my subjects were between 21 and 23. Right? Here, all my subjects were 27. But these same standard deviations may be different if I'm talking about blood lactate, because a difference of 1.16 blood lactate is a lot. So the interpretation really depends on the unit. So there's no set standard. Consider the unit. However, in addition to looking at the unit, the use of standard deviation allows us to chunk data. And this is what I said at the beginning and maybe what you've heard of. In a normal distribution, in a bell-shaped curve, because it's bell-shaped, we would expect most of our data points to fit towards the middle. So we can chunk these into a more standardized way. So these are like talking about two separate things. When I'm talking about reporting it in a paper, this is what it looks like, right? I give my mean plus or minus standard deviation in a unit. But from a theoretical standpoint, we've come up with these standardized probability segments. So theoretically, we've developed this system so that we have our mean, and then we look at plus or minus 1 standard deviation, plus or minus 2 standard deviations, and plus or minus 3 standard deviations. The way that we calculate standard deviation, we run probabilities. So behind the scenes, people have run all these probabilities, and from that, they have come up with the formula for standard deviation. And theoretically, by using that formula to calculate standard deviation in units of that particular variable, theoretically what it's telling us is all of the data points that fall within plus or minus 1 standard deviation represent 68% of the data. Again, these are standardized, plus or minus 1. This is a different way of looking at it than when we actually report it for each variable. Theoretically, we look at plus or minus 2 standard deviations includes 95% of the data. And then lastly, plus or minus 3 standard deviations includes 99% of the data. So you might see this thought of differently. In a particular research study, you're going to report for your individual variables mean plus or minus standard deviation in that unit. Here's an example: age. Group A, the mean age was 22.67 years, plus or minus 1.16 years. And what this is representing is 1 standard deviation. So if I were to map this out, as we will later, I would put my mean, 22.67, and then plus or minus 1 standard deviation would be 22.67 minus 1.16. What's that? 21.06. If I did the math wrong, sorry. And then plus would be 23.73, right? So that's how you would calculate it moving out. And then if I went here to our second one, it would be 21.06, again, minus 1.16. But really, that's getting into the weeds that we'll talk about more later. This video is all about just introducing it, okay? Cool. All right, when we see it reported in SPSS, you'll often see the standard deviation reported. You might see the variance next to it. We care about both numbers in terms of statistics. I'm going to report standard deviation, but when I go on to do further inferential stats like t-tests, ANOVAs, I'm going to be using variance. And all variance is standard deviation squared. So if I take 4.7668 and I square it, I get 22.7222. So we've already said you should report central tendency and a measure of variance, like mean plus standard deviation. Behind the scenes, when I go to run inferential stats, I'm going to have to use variance. And there's a reason why. So when we go from descriptive to inferential, right? In inferential statistics, we're trying to make conclusions or look for relationships. So we're looking at all of the data points. Mathematically, if I'm looking at all the data points, right? Here's my mean, and I have all these data points. One thing that we're going to need to do to run the inferential statistics is to calculate the total variance. So in addition to looking at how much each individual score varied from the mean, right? This X varied that much from the mean, but this X varied this much from the mean. That's each individual score from the mean. But if I take the total variance, if I look at each data point minus the mean, and I add that up, I get 0. Right? If we add up the distance of each data point from the mean, I'm going to get 0. And that is not useful for me mathematically, right? How can I get an idea of total variance if it's always going to be 0? So simply said, folks, that's why we use variance. By squaring each distance from the mean and then adding up that, it gives us a value, a numerical value that we're actually able to use. That's something called the sum of squares. We sum the distance of each point from the mean squared, and we get our sum of squares. Just means we use variance because we square it. But that's behind the scenes. Pretty cool, though. Just think about how smart you're getting. All right. We can also utilize visual representations of these measures of variance, right? Standard deviation and variance. So a good example of that is an error bar. And here's a good example. So here we're seeing a visual representation of vertical jump heights in centimeters across gender identity. So in cisgender males, the average vertical jump height in centimeters was about, 47 centimeters. In cisgender females, the average was about, 32. And then in transgender females, which is a better way instead of male to female, in transgender females, it was about 33. That gives us the mean. But these error bars have this. And that tells us the standard error or standard deviation. So if the mean is in the middle, this simple error bar shows me the total range or the standard deviation. Not the total range, pardon me. It shows me the standard deviation. The average variance was, just from looking at this, it looks like the average variance was 3 centimeters, but it was a smaller variance here because the error bar is smaller. It was a higher variance here. So a nice visual representation, and these are sometimes called whiskers. It shows us, in addition to showing us the mean, which is where the bar comes up to, it shows us the variance around that mean. It shows us what one standard deviation around that mean is. A wider whisker tells us there was more variation. A smaller whisker tells us there was less variation. Fantastic. You may also use box plots, or sometimes called a box whisker diagram. This is a nice diagram explaining it. This is something that you would use for data screening. You would not use it in your report. I would use this in my report. I would only use this as a way to better understand my data and screen it further if needed. Okay. So we've talked about summaries of data, we've talked about measures of central tendency, and we've even talked about standard deviation, which now, you got it, folks. Standard deviation is average variability of scores about a mean. The mean just tells us the average, but the standard deviation tells us how much the other scores vary from that average. High standard deviation means that the other data points vary a lot from the mean. Lower standard deviation tells us that the other data points do not vary much from the mean and they're closer to the mean. Our last example of a descriptive statistic would be a category known as measures of position. Percentiles, folks, that's what it is. And we're almost done, look at that. Any type of measure of position compares one score to a group or an entire data set. The best example of this would be like SATs or GREs, right? You get your results and you see the percentile. It's a comparison of your score to either a group. You can look at your percentile of how you did in relation to your state, or you could compare your one score to the entire data set. What's your percentile nationwide? Oh, hi, Bob Ross, you're back. We're describing things like that beautiful tree that you painted. Percentiles will give it to us on a scale from 1 to 100. Deciles, as the prefix suggests, how one score is positioned among 10% groups. And quartiles, as the name suggests, how one score is positioned among 25% groups. When I was studying way back when, this is something that I came up with to understand better. So imagine a scale going from 1 to 100. I didn't want to make one that big, but 1 to 100. So maybe you get your verbal scores back from your SAT or GRE, and you are at the 85th percentile. That means that if we line up all of the scores from lowest to highest, you're about 85%, which means that you scored better than 84%. But you scored lower than 16%, 14%. Yeah. Or maybe they break it down in deciles, right? Maybe they look at 10% increments. That can sometimes be useful when you're trying to compare groups or regions, like I said, states. And we can do quartiles. We can break down information into what data points fell within the Q4. So if you were 85% individually, you're definitely Q4. If you fell with between 51 and 75%, maybe you were within Q3. These all can be useful. And in SPSS, you might see something like this where we get a percentiles written out. These would be quartiles. It shows me of our data, how many fit within the 25% quartile, how many data points fit within the 50, and how many data points fit within the 75. Here's an actual thing about the GREs. So here's how they grade you. So these would be the scores here. And then based on your score, what percentile you fit into. Okay, so really only useful when it comes to generalized tests, things like that. All right, folks, hope you learned something here. Don't take this for granted. Hopefully I didn't lull you into sleep with the Bob Ross, but descriptive statistics, really important. Great job.